Welcome back to this fourth video in the series on how to do quantum mechanics using programming. In this video, we're going to be looking at operators and how they're connected with observables, and we're going to compute observables and operators using Python. As always, if you like this video and would like to share it, like it to reach more people, then please like it, share it, subscribe, and comment in the comment sections. So in the last video, I gave you an exercise to create a Python function which takes psi as an input and then returns the psi dx. So let's have a look at how that is done. I'm just going to install confit again in this new environment. To do this, we're going to be creating a function and we're going to call it ddx, for instance. And as I said, it's going to take psi as an input, and it's going to calculate the derivative of psi. Now you can either do this using some sort of numerical loop where you loop through all of the points and calculate the differences, but I am simply going to be using the just the numpy gradient function. So first of all, let's do import confit as cf, import numpy as mp. These we're going to need. And then I'm going to create my system, cf.quantum mechanics 1, and then I'm going to put xlim between -10 and 10. And I'm actually also all right, let's keep it that way. I'm also actually going to set the resolution to be 100. I'm just preemptively thinking something. So what I'm doing here is that I'm setting that that should be from -10 to 10, and then the resolution should be 100. I just want to check, why did I do that? I think I did that because I wanted QM dx to be exactly 0.2, and I was right in that, so that's fine. Okay, so I'm going to create my function ddx. It's going to take psi as an input, and then as I said, there are several ways of doing it. What I'm going to do is I'm simply going to return numpy.gradient, which is a function that does this. So returns the gradient of an n-dimensional array, blah, blah, blah. Parameters, it takes an array. So that's going to be our psi field, the one that we passed as an argument. And then it also says varargs list of scalar array optional. And the first is the spacing between the values. So spacing can be used single scalar to specify a sample distance for all different dimensions. And that's exactly what I want to do. So I'm going to do qm.dx. So now I have created my function here. And then if I try, for instance, to calculate, well, I haven't configured qm.psi yet. So if I try to write qm.psi, well, it's giving me nothing actually. So if I print it, you see that it hasn't been defined yet. So I need to define it. And since we're going to be using a lot of Gaussians, as always, we're going to be configuring initial condition Gaussian with a width of 1. So now we have qm.psi, and now I can write dpsi dx is equal to ddx of qm.psi. Then I get something. It's probably just going to be an array, right, with numbers. It's real numbers because this initial function that we created was fully real. So let's just give it a velocity so that it's not a completely real function. So I now calculate this. It still works. But now you see that deep psi dx is actually an array of complex numbers, which is going to be useful. I could plot it if I wanted to. So plot complex field deep psi dx, and then I write index 0 just to get the fig element of this function. And then you kind of see that it looks like this. It actually looks quite a lot like the initial function that we had. Yeah. So that's that. I wonder what if I don't give it an initial velocity, then it looks kind of different. The function looks different. All right, makes sense. Okay, so so that was the exercise, and we're going to use this because we're going to be talking about observables and expectation values in this video. So what are observables? Observables is a term for things that we can observe, meaning measure. Meaning that like position is something that we can measure, momentum is something that we can measure, and the energy is something that we can measure. And then the question is like, given this wave function, this complex state, how can we use this to predict what we will measure from it? How do we get from this to observables? And we already know one method, right? So, well, not really, because what we have so far is the Born rule, which told us something about what was the probability of measuring the particle somewhere. It didn't tell us anything about the outcome, really, unless you know what the limits of that is. So in order to get observables from the wave function, we need something called operators. Now, an operator is something which takes a function, a wave function, as an input and applies the operator onto it, and then out you get another complex field. Now, this output is not necessarily a wave function. And the reason for that is that if I take what comes out of here, it's not necessarily something that when I integrate it turns to 1. So in general, when you apply an operator to a wave function, you do not get a wave function out, but you get another complex field, which we will use to calculate observables. So an example of an operator is what we call the position operator, which we denote by x and a hat. So operators are typically denoted with hats. And so if I do that, I get psi x psi, which is if I just write it out as a complex field, is just x times the wave function. So what we're going to do now in the programming is we're going to implement the position operator, and we're going to verify that x psi is no wave function. And you can try to do that before me if you're motivated, or you can just watch. So we've already implemented one operator already, actually, this one. So we're just going to do the same thing. So def, and then let's write it as x hat psi. That's the position operator. And then we're just going to return qm.x multiplied by psi. Simple as that. So now we've implemented the position operator. And if I implement that, if I apply the position operator to the wave function x hat of qm.psi, I am getting a complex field. And how do I know that? Because if I print it, I can see that this is essentially just an array of numbers. And if I want, I can plot this field like so. And we can see that my initial wave function didn't look like this. Let's just have a look at the thing that I started with. So the initial wave function, it looked like this. And then I applied the position operator onto this wave function. And when I plot it, it looks like this. And we were also going to verify that this thing here is not necessarily a wave function itself because it's not normalizable. So to verify that, I'm going to do qm.calc integrate field. And then I'm going to take the absolute value of this object and square it. And I actually got 1, which is a bit surprising, but I do think it's purely a coincidence due to like the fact that we're using these whole numbers like 1 and 2 and stuff. So I think if I use a different initial wave function, I just need to check this now. Let's say we set the initial velocity to 0.2 instead. So here's our initial wave function. It's sort of less, it has like this complex phase gradient here, but it's not as much. Then we apply x hat to it and we plot the wave function. Looks like this. And then we integrate. We still get 1. Why do we get 1 here? Oh, maybe it's because of the width of the initial wave function. I think there's something random about like the width here. So if I instead do 2, and then I define this. So now my initial wave function is much wider. Is it? Yeah, now my initial wave function is much wider. And now if I integrate this thing, it does not give me 2, which is what I wanted to show. So in fact, this x psi thing here is not something that is a wave function because it doesn't necessarily integrate to 1 when taking the absolute value square. Now, in this simulation, when I used width equal to 1, there was like some numerical coincidence that made it so that it actually did integrate to 1. So it could represent an actual physical state, but in general, as you see, if the wave function is not exactly that, then you get something else, which is what we see here. So that's the position operator. Now, the next operator, or there's sort of 2 important operators. One is the position operator, and the other is the momentum operator. If you go to Wikipedia and you look up the momentum operator, you will find this expression here. So p hat is equal to minus I times d dx. So it's the same thing. The operator takes in a wave function and out pops a different object, which is not necessarily a wave function. So in this case, it's minus I times the derivative of psi with respect to x. So now let's implement the momentum operator 2. I am going to use this initial Gaussian wave function with width equal to 1. I don't like it when it's too wide. So let's define p hat, takes psi as an input. As we look at it, I need to have minus the imaginary unit, so minus 1j times, and then it's the derivative of psi with respect to x. And we've already done this previously, so I'm going to write n dot gradient psi and then qm dot dx. So here I have defined p hat, the function, and now I can apply this to psi by writing, yes, and Gemini is expecting what I want it to do. So this gives me something which could or could not be, or it's generally not a wave function itself, but we can plot it if we want to. qm.plot complex field, p psi 0, and we see that we get something different. So after applying this differential operator, we get something strange. And just to verify, is this a wave function? I mean, let's try to see what we get. So qm.calc integrate field, p psi, and take the absolute value of that squared, we get something which is not 1, which means that it cannot be a wave function. So those are operators, but the question then is like, how do we get from these operators to observables, things that we can observe? And the way to do that is through this thing called expectation values. So the expectation value of something is when you have like a probability of measuring something, and then you measure something again and again and again and again, then the expectation value is going to be the average of that measurements after you've done it many times. And usually when you have a probability distribution, the way to calculate, for instance, the expectation value of this observable x is that you integrate the outcome with the probability density over the whole of space. Now, we know that in quantum mechanics, the probability distribution or this probability density is given by the absolute value of the wave function squared, which means that I can write it like this if I just write psi conjugate multiplied by psi. So remember, this goes back to the first video on the complex fields, that the absolute value squared is equal to the complex conjugate multiplied by psi. And the reason that I've placed x in the middle is that because this sort of structure of the complex of the expectation value calculated from a wave function is general, so it's going to look the same all the time. So given this, let's now go to programming and calculate the expectation value of x. So what I need to calculate is I need to integrate this thing here. I'm going to do now, in order to get, remember, qm.psi, that's an array of complex numbers. If I want to get the complex conjugate of that, I can use the numpy function called np.conj. This is going to give me the complex conjugate of psi. Then I need to multiply with the x operator acting on the psi field. So x hat of qm.psi. So what I have here is this array inside the integrand, and in order to integrate this, I need to pull up the function calc integrate field, and then do this whole thing here. And what you see is that the number I get in the end is a complex number, but the imaginary part is very small, 8.35. Actually, like if this is done correctly, like ideally, when you calculate the expectation values of some observables, you should get a real number. The reason that I don't get a real number here is because we're doing numerics, and then you'll always be left with some like small imaginary part, which is not there. Now, the real part here, however, is 8.88 times 10 to the negative 6/17, which is basically 0, which means that the expectation value for the x operator is 0. And that actually makes a lot of sense, because if we plot the wave function, you can see that the wave function is actually centered around 0. So we expect to find the particle at position 0. So that's the expectation value. If, for instance, I were to start with a different wave function, so let's say I did qm.conf initial condition, let's say I put position equal to 1 and then initial velocity equal to 0.2 again. Now the wave function looks different, and it's also very wide, so I also want the width to be 1. Now the wave function is located here, and then therefore, if I calculate this integral here again, now you can see that actually the expectation value, or the real part of the expectation value of x, is 1 here. And again, the imaginary part is just there and it's very small. We can remove it simply by writing point real. And then we can see that like the expectation value for the position is 1, which is what we're seeing here. Again, if I change it to 0.5 or 0.2, and then I rerun the code that integrates, I get that the expectation value for x is 0.2. Now the same expression for the expectation value of x can be used to calculate the expectation value of the momentum, and it's the same thing, right? So the expectation value of p is equal to, and then we use the same formula as here, only now we replace the p hat with the operator. And the reason that I'm writing like this is a little sloppy is that usually I'm sort of mixing between like looking at this as if I'm writing p as like a general operator, but I'm also just replacing it with this I ddx. Some might call it sloppy, but we're interested in programming here, so I'm going to continue with that. So I have psi conjugates times this thing here, p applied to psi dx. So now let's use this function to this expression to calculate the expectation value of the momentum, and it's actually going to look very similar. The only difference is that instead of acting with x operator on psi, I'm going to act with p, and what I get is 0.19. Yeah, and just as a sanity check, again, you see that actually in this case it got 0 exactly for the imaginary part. That's good. But let's just take the real part, because we know that the observable is going to be real. We get 0.198, which is almost 0.2, and that is in fact the initial velocity that I gave the momentum. So if I increase the initial velocity to 0.5, the wave function looks like this. And if I calculate the expectation value for the momentum, then I get almost 0.5. So that is in fact the way in which this plane wave gives this function its velocity. Now, while we are at it, looking at this operator, this x operator and the p operator, we can have a look at the what is called the commutation relation between the x and the p operator. So, according to quantum mechanics, the commutation relation between x and p is given by I h bar, where the commutation between these two operators is essentially AB and then subtract BA. In the case of our simulations, we're always working with dimensionless units, so we're putting h bar equal to 1, which means that we are expecting that xp minus px is going to be equal to I. And I wanted to verify this with the program, but we need to understand what that means. So what it means is that if I first apply xp, so in this order, so first apply p to f and then apply x, and then I subtract the thing that I get if I first apply x and then subtract and then apply p, then I'm supposed to get I times the function back. That is what the commutation relation is saying. And since we're doing programming, we can try to verify this with our functions. So how do we do that? Well, first of all, let us just see what it looks like if we multiply a function with I. So let's start with configuring a Gaussian here. Initial condition Gaussian and we're going to place it at the center with no velocity and just have a look at how it looks like. So here you can see this wave function, and it's centered at 0. The phase is just 0 everywhere, which means that this is just a positive number. So what does it mean if I multiply this? If I start with f of x and multiply by I can have a look. So if I do 1I times qm dot psi, it essentially just shifts the phase from 0 to pi over 2. So 0.2, 0.5 pi. So in order to verify the commutation relation, we need to calculate the left-hand side here, acting on some kind of function, and then verify that the result of doing this operation is the same as just multiplying by I. And we know what multiplying by I does. It just shifts the phase with pi over 2. So now let's do that. So we're going to do x hat of, and let's do this in the right order. So first we apply p, then we apply x. So we apply p onto qm dot psi. Then we apply x hat to that result. Then we subtract the other way around. And now Gemini is actually suspecting what I'm trying to do here. So this is the left-hand side of this equation. And we expect that if I plot this thing, it's going to give me the same thing as if I just multiplied by 1j. So let's try to just plot that. Dot plot complex field. And add 0 to extract the fig object from the plot function. If everything goes correctly, we should get the same thing, and that's exactly what we get. Now, is it because of the initial wave function? Well, we could try to move it to like 3 to give it some different starting point and give it like a different initial velocity. So now the wave function looks like this. The result of multiplying that function by I is essentially just shifting the phase all over the place to this by pi over 2 shifted. And then if the commutation relation holds, then we're supposed to see the same thing when we apply these two in this order. And that is exactly what we see. Now, it should be said that like this is not a formal proof. This is just us verifying the commutation relation with numerics. And there are many tutorials on YouTube that proves this analytically. So I recommend that you go and check one of those out if you find that strange. But at least our program shows us that this works. So that sort of concludes this video. For the next video, I would like you to try to calculate the expectation value of x squared and also the expectation value of p squared. And to do that, you need to apply the operator not once, but twice in each case, and then do the same thing. And so good luck with that, and I will see you in the next video.